Okay, class, we are going to take a look at section 6.4 notes today, which is going to be an introduction to writing systems of equations as an augmented matrix and then putting them into row echelon form and reduced row echelon form to come up with the solutions to those systems. I'm not going to introduce the graphing calculator method quite yet. What we're really going to mostly be concerned about as far as doing the row echelon, reduced row echelon is just some of the row operations and being able to do a few of those. I'll explain that in more detail as we get to those examples. Okay. So a matrix is just a rectangular array of elements. It's usually enclosed by brackets, just like this, and dimensions are given. Now, well, these first three are all square, so it's rows by columns. So 2 rows, 2 columns. Here we have 3 rows, 3 columns. This one's a 4 by 4. Now this one, it's 2 rows, so it's a 2 by 3 columns. So it's always rows first, then columns second as you give the dimensions. Okay, so they explain that here. The dimensions of a matrix M by N would be M rows, N columns. A square matrix obviously has the same number of rows and columns. Matrices are frequently used to represent systems of linear equations. Okay, so it says express each linear system with an augmented matrix. Okay, so the way that we do that, the reason a matrix is nice to use is because you can eliminate the variables from it and you just work with the coefficients. So in this, they're easy to translate into a matrix. So what we would do here is we would just take coefficients 2, -5, 6, and then the -3 would go here, and then we'd have 3, 7, -3, and 8, and then we have 1x, 7y there, and we have nothing here, so we fill in a 0, and we've got 5 here. Now in an augmented matrix, there's a vertical bar that goes where all the equal signs are. That's called an augmented matrix, and that's what we would use for solving a system of linear equations like this. And to do that, we'd want to put it into either row echelon form or reduced row echelon form. And we can do that with our calculator, but we are going to work on just a few of the row operations by hand and just take a look at how that's done. Okay, here it says write the linear system represented here. So this is just kind of going in reverse of what we had done before. And so if we write this back as a system of linear equations, we would have, you know, the first row 1, 2, 3, and -4. So that's 1x plus 2y plus 3z equals -4. And then here we don't have a term for the 0, so then we just have y minus 6z equals 7. And finally we have just z equals 8 at the bottom. Okay, so that would be kind of going the other direction with it. All right. So start talking about what row echelon form is. So they give us several matrices that are in what's called row echelon form. To solve linear systems with augmented matrices, a convenient form is row echelon form. Each of the following matrices below are in row echelon form. So what you're going to notice is that they call it the main diagonal. So the main diagonal always contains 1s or possibly 0s. And then below each of those in the main diagonal, the 1s or possibly 0s, there's 0s below those. Okay, so we can see these are all in. So here we do have some 0s in the main diagonal. When that happens, what we see is that's a kind of a different type of system of equations, which means there's either going to be infinite solutions or no solutions when you see a 0 appear in the main diagonal. Okay, and so these are all considered row echelon form. Okay, and they do explain that a little bit more in detail here. The elements of the main diagonal are blue in each matrix. Scanning down the main diagonal of a matrix in row echelon form, we see that this diagonal contains only 1s, possibly some 0s. Like I said, if there are 0s, we know that it's going to be a situation where you have an infinite number of solutions or possibly no solutions. Okay, and like here, for example, if we have 0 equals 0, that's going to be a true statement, meaning that there's going to be an infinite number of solutions. Okay, if we would have 0 here and then some other number like 1, that's going to be a situation where we have no solution. Okay, so again, so row echelon form, the first non-zero element in each non-zero row is a 1, and that one is called the leading one. If two rows contain a leading one, then the row with the leftmost leading one is listed first in the matrix. And so what they mean, so you want to put this one here first. Rows containing only zeros would occur last, so if you do have a row that contains only zeros, that would be the bottom row. Okay, so it says solve the system of linear equations represented by the augmented matrix. So if we're going to solve this system, and it's already put into row echelon form for us, so the reason that that's convenient for solving is because if you start on this bottom row, really what this is saying, and so let's just write it out with our variables, just to write them all out. So I'd have 1x plus 1y plus 3z equals 12 for the top row, and that translates into that equation. And then there's a 0, 1, negative 2, negative 4, so that means we have 1y minus 2z equals negative 4. And then finally for the bottom, I just have a 1 right here in the z position, so that's just going to be z equals 3. And so the good thing about this is that this bottom equation is already solved for one of the variables. So then at that point, all you have to do is back substitute into the equation above it, and put the 3 in for the z, and then I can solve for the y. And then I'll have both z and y, put those up here, and then you can solve for x. So knowing that z is equal to 3, I can take 3 and I can plug it in right there. And so when I do that, I'll have y minus 2 times 3 equals negative 4. And so then y minus 6 equals negative 4. And then I'm going to add 6 to negative 4, so y would equal 2. So now I've got two of the variables. I've got that z equals 3 and that y equals 2. So now I can take those both and I can put those up into the top one. So z equals 3 there and y equals 2. And I'll change colors again. So if I do that, I'm going to have x plus 2 and then plus 3 times 3 equals 12. I'm going to solve that equation. So that's x plus, and then 2 plus 9 would be 11 equals 12. And then x would equal 1 if I solve that. So as it turns out, then I get x equals 1, y equals 2, and z equals 3. So I'd write my answer as they call it an ordered triple. 1, 2, 3. Okay. So once you have it in row echelon form, like they do, you know what z is equal to. It's that, it's going to always be this bottom number here. And then you just back substitute, get your y value, and then substitute again up into the top equation to get your x value. Okay. The process of putting these matrices into row echelon form is called Gaussian elimination. The mathematician Carl Friedrich Gauss, apparently came up with this process. So this Gaussian elimination with backward substitution, if an augmented matrix is not in row echelon form, it can be transformed to row echelon form by using this process. Okay, it basically uses three basic matrix row transformations, and so the three that we can use would be listed here. So for any augmented matrix representing a system of linear equations, the following row transformations result in equivalent systems of linear equations. So we can always just interchange any two rows, because the order that the equations are written in doesn't really matter, but it's convenient to interchange them sometimes to get your ones and zeros in the right spots. Okay, the elements of any row can be multiplied by a non-zero constant, so we can multiply, it's like multiplying both sides of the equation by the same number, so we know that creates equivalent equations. So we can do that, and then also we can, just like when you use the elimination method for solving systems, you can add or subtract, any two, corresponding elements, or, of the systems of equations, or of that would be the rows of the matrices. You can add them or subtract them. Okay, so it says here to use Gaussian elimination with backward substitution to solve. So this process is very tedious and time-consuming. So we're not going to do this like completely from scratch. What I want you to be familiar with is just to be able to perform a few of these row operations that they ask you to do. And so I'm just going to kind of walk through a few. They have it worked out in the following slide. So we're going to kind of just look at the process of how this works, and just so that you can do some of the row operations that you're asked to do and I'll explain that a little bit more in detail. But okay, so the first thing we're going to do is transform this into our augmented matrix, and that's been done here below. So we just take those coefficients from that original, so this, what we have there is the same here. So we have our 1, 1, 1, 1 on top, negative 1, 1, 1, 5, and then 0, 1, 2, and 5. Okay, so just taking those, and that's what we've got here to start. Okay, so that's simple enough, I think. Now they're going to have us do, now this is what I would have, what I want you to be responsible for knowing how to do. So like if the directions were like, okay, this is our matrix that we're starting with. Now, to make a change to it, I want you to take row 2 plus row 1, and they're going to point right here, so that means this is going to be our new row 2. It's going to be achieved by doing those back here on this matrix. So I want to take row 2 plus row 1, and that's what's going to give me these numbers right here. Everything else is going to stay the same, so these ones all stay the same. These numbers right here, they all stay the same in the bottom. But to get a new row 2, I'm adding row 2 plus row 1, because I can add or subtract any two rows. So if I do that, row 2 plus row 1, negative 1 plus 1, that's why I have 0 here. Okay? And then it's going to be 1 plus 1, that's a 2. I'm going to have 1 plus 1 again, that's also 2. And then 5 plus 1, and that's 6. So that's how I get that new row. Now on the quiz, you will have to do a couple of these types of things where they ask you to add two rows together, okay? Or possibly like this, okay? Now, the next thing they're going to ask us to do, we added those together because we needed a 0 here. We needed to get a 0 in this position because after you have this 1, we need zeros below it. Okay, so that's why we added those together. Now the next thing we want to do, see they have this one highlighted. We want to make a 1 here next because we need 1s in our main diagonal. So what we can do then is we can multiply any non-zero constant times a row. And if we multiply by a 1/2, that's going to create a 1 there. So that's what we're doing here. So it says 1/2 times row 2. So you think, okay, I'm multiplying each one of these elements times 1/2. So 0 times 1/2 is still 0. 2 times 1/2 is 1. 2 times 1/2 is 1. And 6 times 1/2 is 3. Okay, so that's how we got that new row 2. All right, now it highlights this one in blue. That means we're going to concentrate on this one to make it a 0 because I need this to be a 0. So how can I make that a 0? Well, I've got numbers that are the same up above it, right? So I've got 1s here. So if I subtract row 3 minus row 2, well, that's going to give me a 0 though. So that's what they're asking me to do here. So if I go back to this one, so row 3 minus row 2. Corresponding elements, 0 minus 0, that's still 0. 1 minus 1, that's 0. 2 minus 1, that's 1. And then 5 minus 3, that's 2. Okay, so now I've got it into row echelon form, right? So I've got it to this point now where I have 1, equal, so that's z equals 2. So now I know that that's the case, right? So I could solve it at this point. So now that I've got it in row echelon form, this equation is going to read x plus y plus z equals 1. Then it's going to be y plus z equals 3. And then finally z equals 2. Okay, so I've got that. Now I'm going to do my back substituting like I did before. So z equals 2. I'm going to take 2. I'm going to plug it right up in there. And so that's going to be now y plus 2 equals 3. And I subtract 2. Y would equal 1, right? And now I need to substitute both of these numbers. I need to put 2 in for this z up here, and then I need to put 1 in for this y up here so that I can solve for x. Okay, so it's going to be x plus 1 plus 2 equals 1. So that's x plus 3 equals 1. Subtract 3, x equals negative 2. Okay, so now I've got them all. I've got x equals negative 2. I've got y equals 1, and I've got z equals 2. So my ordered triple then, negative 2 for x, 1 for y, and 2 for z. Okay, so that would be my solution. All right, so once you get into this row echelon form, then we can solve it fairly simply because we already know what z is, and then we just have to back substitute twice. Some geometric interpretations here. The idea is that when you're solving a system of equations in just two variables, it's pretty straightforward. It's either like two lines that intersect in a point and you just get the one ordered pair for the solution. The other thing that can happen is you can have parallel lines, which means you have no solutions, or you can have one line right on top of the other line, and then that's where you have infinite solutions, right? Now, when we're talking ordered triples, what you're representing, instead of lines, you're actually representing a plane, like a plane that's in space, in three-dimensional space. Lines are just on a two-dimensional plane. Now we're talking three variables. So if we're going to kind of visually interpret this geometrically, we'd be thinking of the intersection of planes. Now, it is possible for planes to intersect in one ordered pair, and that's what we've seen on our last two that we solved. So ordered triple, I shouldn't say ordered pair. It is just a point in space, but it's a point in three-dimensional space instead of in two-dimensional space. Okay, so you need, like an x, y, and a z axis to locate a point in space. Now, it is possible to have an infinite number of solutions, like planes could all intersect in a line, possibly, right? You could also have, all the same equation where all points are in common, which that would be just different forms of the same equation. It's possible you have no solutions because maybe you have parallel planes. It's also possible you have no solutions because two of them are parallel and another one cuts through in a different way. Here's another way that you could have no solution, where you have no points in common. Okay, then the final thing we're going to talk about just a little bit is, so there's row echelon form and then there's reduced row echelon form. If you're looking on your calculator, if you've done this before, row echelon form, they have like R, E, F on one of the choices there. And reduced row echelon form is R, R, E, F. Okay. Now, reduced row echelon form it's actually way easier because then the solutions are basically just the last numbers, the last column there. But if you're doing it by hand, then it's more work to put it into that form. But the idea is that every element of the main diagonal is either a 1 or a 0, and then every element either above or below, below we had zeros before, but either below or above is also a 0, okay? So if that is the case, then we've got reduced row echelon form, okay? And then, it was Gaussian elimination for row echelon form. Yeah, this isn't all that important, but Gauss-Jordan, so another mathematician, kind of teamed up with him on this to put it into reduced row echelon form. Okay, so just it says use Gauss-Jordan elimination to solve this system, meaning to put it into reduced row echelon form. So the first thing that we would start by doing is, again, just transferring this into our matrix, our augmented matrix, and then just doing some of these row operations. I'm going to just go to the next page because kind of started it over there, and I just want you to try to follow this because you will have to do a few of these operations. So the first thing we did was swapped rows because we wanted to get, let's see here, so we flipped row 1 and row 2 around, it looks like, okay, because we want to have a 1 in this upper left hand position first. So row 1 and row 2 just swap right there, so that's pretty easy, okay. And then the next thing that we're going to do to create, and then it's just rewritten again here. So they're starting with this one. So to get a new row 2, what we want to do is take row 2 minus 2 times row 1. So let's just kind of walk through that. So row 2 minus 2 times row 1, because we're going to try to get a 0 below this one, okay? So that's how we're going to get this new row 2. So let's go back to this one. So row 2 minus 2 times this number up here in row 1. So that's going to be 2 minus 2 times 1. So that's how we get 0, right? 2 minus 2. That's why I have a 0 there now, okay? Same thing. 1 minus 2 times 0. Well, that's still 1 minus 0. That's still 1 right there. 2 minus 2 times 2. So that's 2 minus 4. That's why that's negative 2. And then 10 minus 2 times 5. So that's 10 minus 10. So that's why that's 0. Okay? So an operation like this, that would be something you'd have to do on the quiz. Okay? They'll tell you to do this. You have to go to the previous matrix and just do whatever they're saying. Row 2 element minus 2 times row 1 element. Pretty simple, okay? And then for this one, for the new row 3 here, we're taking row 3 minus row 1. Okay, so row 3 element minus the row 1 element. 1 minus 1, that's 0. Negative 2 minus 0, that's still negative 2. 2 minus 2, 0. And 1 minus 5, negative 4. Okay, so now look at what we've done so far. We created a 1 up here and we got zeros below it. So that's what we want to see happening. Okay, now we've already got a 0 above this one. We want to get a 0 below here. So that's why we're going to concentrate on this one and changing that to a 0 next. Okay, so as we do this, so I've got some of this blanked out here. So see if we can kind of get through this last part of this here together. So what we want to do next is we want to, it says we want to take row 3 plus 2 times row 2. Okay, so let's do that. So row 3 plus 2 times row 2. So in the previous matrix that we had right here, row 3 plus 2 times row 2. So that's going to be 0 plus 2 times 0. We still have 0 right there, and that's what we want to keep. Okay, so then go back here. Negative 2 plus 2 times 1. Okay, so that's negative 2 plus 2. That's going to give me 0 right there, and that's what I wanted for that one as well. Okay, and then row 3 plus 2 times. So 0 plus 2 times negative 2. 0 plus 2 times negative 2 is 0 plus negative 4. So I get negative 4 there. And then finally, negative 4 plus 2 times 0. Well, that's still going to be negative 4. Let me see if I said, yeah. Okay, so that's what we have in that step. Okay, so that was just taking row 3 plus 2 times row 2. Back from the, we always go from the previous matrix. Okay, so then we came up with those numbers. So now we've got zeros in the appropriate spots there. Okay, now the next thing that we wanted to do here was we want this position to also be a 1. Okay, where this negative 4 is right here in the main diagonal, that needs to be a positive 1. So that's why we're going to take negative 1/4 times row 3. Okay, because that's going to get what we want out of that. That'll change both of these negative 4s into positive 1s. Okay. All right, so we're real close now. Finally, we're gonna need to create zeros here and here, and so to do that, we're taking, so in this top row, we're gonna take row 1 minus twice row 3. So that's be row 1 minus 2 times row 3. So that 1's gonna stay the same. That 0's gonna stay the same. So row 1 minus 2 times 1, right? So that's going to be 2 minus 2 times 1. 2 minus 2 is 0. So that gives us 0 in that position now. And then we're going to have 5 minus 2 times 1. So 5 minus 2 is 3. So we have 3 there now. Okay? So now we've got zeros, you know, where we need them there. This one needs, this negative 2 now needs to become a 0. So to get that, we're going to take row 2 plus 2 times row 3. Okay? Row 2 plus 2 times row 3. So that's still 0 there. That's still, you know, row 2, that's 1 plus 2 times 0, that's still 1 there. Okay, and then here, negative 2 plus 2 times 1. Negative 2 plus 2 can become a 0 there now. Okay, and then finally we've got row 2, 0 plus 2 times 1. 0 plus 2, that's why that becomes 2. Now we've got it all the way into reduced row echelon form, so that's easy to, we see that in z equals 1. We see that right here then, y equals 2, and for this one, we'd have x equals 3. So it's, once you get it there, these are just your solutions. This is x, this is y, this is z. Okay, I think that is all. Okay, so that's an introduction to solving systems using matrices with row echelon form and reduced row echelon form.